So we are studying representations, and so far we're just talking about some general definitions and some generalities related to representations. Let us continue doing that. All right, so let me consider Lie group G, and let G be its Lie algebra, tangent-Lie algebra, as before. And well, by the following, rep G and rep G small. So let this be categories of finite dimensional representations of G and G respectively. So if you're afraid of word category, just data about all representations, finite dimensional, and homomorphisms between them. Okay. Of course, also this has more structure, as we discussed last time. So we can consider tensor product, we can consider direct sum, taking duals. All that says basically that that these two categories are tensor categories, whatever it means. But I mean, this word is actually was invented to just grasp all the structures that we introduced last time. All right, so, and last time we discussed what is homomorphism of representations, and so let phi from V1 to V2 be homomorphism of representations of G. Then, well, what does it mean, right? I have homomorphism from G to endomorphisms of V1, right? Coming with this representation, right? Call it. So V1 comes with homomorphism rho 1 to G of V1, and V2, of course, comes with rho 2, and the fact that it is homomorphism, it's just the following thing, that phi of rho 1 it's rho 2 phi. So I should write some element G here, right? And some element G here. So yeah, so phi is a linear map from V1 to V2, right? And for each G, rho 1 or rho 2 are linear maps on V1 or V2 respectively. So it all makes sense, right? Phi sends V1 to V2. This is something on V2, some transformation. So this is transformation on V1, and then it goes to V2. So these are linear maps from V1 to V2. All right, but then let me take differential of this. So then, if I take differential of this, I will have d phi d rho one so of G, so I should write it like that, equals to D rho 2 of G and D phi. All right. So actually, d phi is just a linear map, right? So so phi is linear map. So d phi is the same as phi, right? So if you take a linear map and consider differential, right? Differential means that you just leave everything, like erase everything except linear terms. So for linear map it doesn't do anything, right? So I have phi d rho 1 of G equals to d rho 2 of G phi. All right. So very good. So what I mean now? Why am I doing this? Is because now phi becomes so to conclude that phi is homomorphism of V1 and V2 as representations of G, right? Because well, we have rho 1 and rho 2, right? If I take differential, then d rho 1 and d rho 2 are well, these are homomorphisms of G small to GLN small, right? So differentials are representation, define me structure of representation of Lie algebra on V1, V2. So representations of G. So all that I need to state that I actually have functor, right? So which for every representation, like from this category to this category. So this functor, I don't know how it's, so it's denoted as Lie in my notes, so let me keep it. And so if I have rho V, like a representation here, then, well, corresponding object in here is this, d rho V, the same representation. And this says that it is really a functor because if I have a morphism between representations, that it becomes a morphism, like an arrow in one category, which is morphism, right? Goes to an arrow in another category. So it's functor. We can say, so if G is connected now, we can say something more about this functor, right? So if G is connected, then so then the second fundamental theorem can be applied, right? Which says that so we have, if we have homomorphism between G1 and G2, right? Yeah, so no, I don't want a second isomorphism theorem. I need something like just a part of it, which is applicable to connected. It says that from here to here, I have map, right, which sends phi to d phi. So then this map is bijective. So if G is connected, then this is bijective. Not bijective, injective, sorry. But for bijectivity, we need, of course, it to be simply connected, right? But for injectivity, injective, we just need it to be connected.
Maybe G1?
Yes. That's true. Well, what does it mean in our setting? So in our setting, G1 is G, right? And G2 is GLV. So have take G1 as G, G2 GLV, where V is our representation, right? And so so therefore this statement says that this functor Li is injective on morphisms if G is connected, right? So functor Li is injective on morphisms if G is connected. So it is injective on morphisms, but that's another on objects, right? But let me. So I would rather. So what I would like to say, let me formulate it as a proposition, is that functor Li is bijective on morphisms. No, not on objects. So we are going to prove it. If of course G is connected. We'll apply this still even for like the second isomorphism theorem in a minute, right? But let us first prove this proposition.
But what changed from objects?
So yeah. So you see here, if G1 is G, G2 is GLV, and hom is representation. So representation is an object in our category, right? It's not. This statement is it's kind of bad from the view of category theory, because, I mean, they really talk more about isomorphism classes rather than, objects. So, but okay, let us leave it here. So I just want to prove this. It means what? That okay, I have phi, right, which is morphism of representations, right? And I say that the same exact phi is of representations of group. And I say that the same exact phi is morphism of representations of algebras, right? So injectivity is obvious, right? So injectivity is obvious. Well, it's just because Li is just is identity on morphisms. Right, it's still, this thing is still here. On the other hand, so what about surjectivity? So, and for injectivity on morphisms, you don't even need the G to be connected, right? Okay. So suppose that I have some homomorphism of representations of Lie algebras, right? So I have something like this, phi composed with d rho 1 of x equals to d rho 2 of x composed with phi. So x is an element of Lie algebra. So rho 1 v1 and rho 2 v2 here are representations of G small. Sorry, d rho 1 and d rho 2. Right. So I really want this object to be in like to be in the image of my functor. So this. All right, and then so in phi satisfies this property. So it means that it is morphism in category rep G small. All right. Then I apply so I apply exponential, right? So phi exp d rho 1 of x equals to exp of d rho 2 of x composed with phi. So this is just so this is exponential of a matrix. So makes sense. And it is a series. So since it commutes, so it's a series in d rho 1 of x, right? So it computes with every term in this series. So still true. Then I'm using functoriality of exponential or naturality. I don't know who likes it in which way better. Which and so I can now write this phi rho 1 exp x equals to phi rho 2, right? Exp x phi. Then let me take any. So I proved that phi is a morphism of representations if I only consider elements which are close enough to identity, right? But now I'm using. I would like to use the fact that G is connected. So therefore, it is generated by neighborhood of identity. Well, our usual trick. And so if I take G in G, then I can write it as follows. G is so exp x1, exp x2, exp xk for some x1, xk in G.
So we use connectedness.
Yeah, so this is because G is connected. And
Why do we suppose that the representations on the Lie algebra are of the form differential of something?
because I really would like it to be, in a sense, in the image of my functor Lie. So I say that okay, I take G, right? So I would like at least to take a representation which isomorphism class, in which isomorphism class I can find representative who is D row of something, right? To have the because I would like it to be in the image of Lie, right? So what I'm saying is that Lie gives me, right? So if I have home between these two, so my initial data is that these are representations of group, and then Lie induces just map from here. So this is G to here. And these are representations of algebra, right? And this map is just identity. So they home in here, and we proved that if I send it to the same exact linear transformation, it will be in home over algebra. Right. So now let me take something in here, right, and see that the same exact transformation is also commutes with the action of group. Okay, so that's what I'm doing. But V1 and V2, in the beginning, they were representations of group. So therefore, they already came with 0, 1, and 0, 2. Okay. All right. Yes. And what's next is clear, right? So if I take phi, so maybe let me write it a little bit lower. So if I take phi of row 1 of G, right, then I express G as this. Row 1 is homomorphism, so therefore I can write it like this. Phi row 1 of exp x1, row 1 of exp x, k. Then with each of it, phi commutes. Well, I shouldn't say it commutes in this sense, right? So 1 should switch to 2, right? So I can write it like this. Exp x1, row 2 exp xk, phi, and then this is just row 2 of G. Okay, so we proved injectivity on morphisms. Okay, Daria, you should help me. So what's the? It is full and faithful. Yes. So smart people say that this functor is full and faithful. So actually, full means it's surjective on morphisms, and faithful is injective.
Did you prove that it is surjective?
Well, we proved that it is a non-trivial part of this. The fact that it's injective, it's just because it's just identity. I mean, it's not. I shouldn't say it's identity. It's just. I mean, it's inclusion, right? So we proved that it's inclusion. Now we proved that it's actually identity, right? All right. So let me. So now let us assume that G is connected, simply connected. So G. So take G to be connected, simply connected. Then, again, using smart people language, rep G is equivalent to rep G small. Well, equivalence, the definition is that, yeah, so you have functor, and then you have the functor that, like, to the other, in the other direction, so that composition is natural to identity functor, right? But there's theorem that says this happens if your functor is full and faithful, and if you have what's called essential surjectivity. So basically, every you hit every isomorphism class by this functor, and this is exactly the second Lie theorem. Okay, so again, so we know that if let's recall it. If G1 is connected, maybe even in this setting without generalities. So I have home G GOV to home G GOV, right? And I send rho to D rho. And so in this case, this map is bijective. So if you have a representation, you can actually integrate it to a representation. If you have a representation of Lie algebra, you can integrate it to a representation of Lie group. All right. So this is our first thing that we should remember from today's is that okay, representations of Lie algebra is the same as representations of connected, simply connected Lie group with this Lie algebra. So basically, if you would like to, all right, then right. On the other hand, I know that if I have Lie group, right, then it is quotient of connected, simply connected Lie group, which is its universal cover, by some discrete subgroup gamma, right? And therefore, each representation, so representation of G, it is the same. So representations of G is the same as representations of G tilde, but not all of them, right? Such that rho of it sends gamma to E. So it factors through this quotient by gamma. Right, so general tactic how to find representations of a Lie group. You take its Lie algebra, and study representations of its Lie algebra. Then it gives you all information about representations of G tilde, and out of that you pick up those that are trivial on gamma, and this will be exactly your representations of G.
For example, a circle is a quotient of R and C. Right?
Yes, yes, yeah, and we will see an example today on the seminar. Very well. Right. So let me move on and give a couple more definitions. So first definition is that it's natural to ask what should be called subrepresentation, right? So then it's clear. So still, let's spell it out. So suppose again, rho V is a representation of a Lie group G. Then I don't know what eta U is a representation. It's called subrepresentation of rho V. So if U is subspace of V and eta is just rho restricted to U. To restrict it, so there's I cannot restrict rho to just any subspace, right? I would like this subspace to be invariant with respect to the action. Then I can restrict, right? So in other words, subrepresentation is a subspace of V which is invariant with respect to the action of group. So if V has no non-zero proper means it's not doesn't coincide with V subrepresentations, then so it's another definition. V is called irreducible. Okay, and then so suppose you take a representation. If it's irreducible, then okay, you're kind of lucky, you can study it. But if it's not, you can find some invariant subspace inside, right? So if you found invariant subspace, your next question is there another subrepresentation such that it completes this invariant subspace to the whole space? Okay, and if it happens for every invariant subspace, you can find complement, which is also a representation. This is called complete reducibility. Okay, so again, another definition. V is completely reducible if and only if for every subrepresentation U inside V there exists let's call it W. It is also subrepresentation of V, and this is important, such that U direct sum V is U direct sum W is V. Okay, so you always, of course, can find again subspace which is complement to V, to U, right? But it's in many cases it's you cannot find it, so it is closed on direction of your group. So if you found, then you're lucky. Actually, it doesn't happen too often. Like if you consider only algebras. In other words, so equivalently, V is completely reducible if it is a direct sum of irreducible representations. Sometimes I will just shorten it and write irrep. Right, so you can find a subrepresentation and complement subrepresentation. Then you do the same inside each summand, and so on until you get only irreducibles in your direct sum. Okay. So questions that usually people ask when they study representations of a Lie group or Lie. So of course, all these definitions can be repeated just in the same way for algebras. Let me not do this. For Lie algebras, similar definitions. So let us now, since we talk about general things, so usually, questions, main questions in representation theory. So if you answer these questions, then you completed all your goals. So first question is to classify, find all isomorphism classes of irreducible representations. Second, you ask yourself whether, is it true that every representation is completely reducible? So, are all representations completely reducible? If you did one and answer for two is yes, then you're done, because every representation is just direct sum of reducibles. You know all irreducibles, so you just know everything about representations. And if not, then third question is to describe what's called composition factors of your representation. So what it means, I guess this third one makes sense So let us think about finite dimensional representations, all right? And for every finite dimensional representation, you can find the chain of subrepresentations. So V1, V2, Vk is V, such that Vi quotient by Vi minus 1 is irreducible. And so you would like to find such chains, and then you maybe you cannot find complement representation to Vi minus 1 in Vi, right? But at least you can consider these factors. All right. So our next plan is to work on number 1 for Lie algebra SL2, because after, like in maybe next semester, after studying some structure theory of Lie algebras, we will classify and construct finite dimensional representations of simple Lie algebras, semi-simple as well, of course. And the building block there is the representation of SL2. So everything starts with SL2 in the kind of. Yes.
Should be, so V1 should be equal V.
Yes. Yes. I wrote. This is right. So this is the largest. Okay. Before that, let me formulate another general and simple thing, but it's fundamental. I kind of skipped it last year, and I had one request not to do this here. So Schur's lemma. Okay, it is. So Schur's lemma. Let's formulate and prove it. So let V and W be two finite dimensional complex representations okay, it can be for group, for algebras, but we will tend more to study representations of algebras. So let me say algebras here of Lie algebra G. Then the following is true if you consider all homomorphisms of these representations, then there's either nothing, so it's either 0 if V is not isomorphic to W, or C if V is isomorphic to W. I mean, it's just, so 1 here is just identity, and then you can multiply it by new number. So that's where this C is. Well, okay, so let's prove it real quick. Right, so what proof? The first observation is that if I have homomorphism of representations, then, of course, kernel of phi is subrepresentation of V, and image of phi is subrepresentation of W. This can be checked very easily. So it's just you act and see that it's still in the image or kernel.
Just invariant subspaces.
Yes, these are invariant subspaces. Yes.
Maybe we should demand that representation should be reducible.
Yes.
Yes. Let finite dimensional complex irreducible representations. You're right. Irreducible. This is important, of course. Yeah, and that's where we're going to use it, right? So kernel of phi then either 0 or v, right? Since it's subrepresentation, v is irreducible. And image of phi is either 0 or w. In other words, phi, it's either phi is 0 or phi is an isomorphism. Which immediately gives us this line, right? So if they are not isomorphic, then phi is just 0. So therefore, hom GVW is 0 if V is not isomorphic to W. And to prove this line, so suppose that they are isomorphic. Right, then, well, I have some isomorphism between V and W, right? And this means that I actually have some isomorphism between these two. Right? Well, just take isomorphism between V and W and compose it with any morphism here, you'll get morphism here. Okay, but what is this thing? So it's just endomorphisms of V onto itself. And so I just take right. So I let me just take something, some E, I don't know. So let me now just consider this. So this is n V. So let me take some element in here. We already, yeah. So let it be phi. So let me choose some element phi in here. Right. It's just a matrix. It's just linear transformation of V. Right, with some additional properties. So it's a linear transformation. We work over C like finite-dimensional complex spaces, so it has at least one eigenvalue, right, and at least one eigenvector. So let phi V be lambda V for some. So there exists, should say, there exists V and V, lambda from C, and V, of course, is not 0, right? Such that this happens, but then I can take this vector V and what's called generate everything by an action of my algebra, right? Since V is irreducible. In other words, so if I just consider this subspace, it is just row of x1, row of xk, all applied to V. That's what I mean by generate, right? Any such sequence, right, where x1, xk lives in G. So this is subrepresentation. But since V is irreducible, we have V is concise with the space, right? So therefore, any vector I can write down as like that. So let me take I don't know, some W for any W in V, we can write W like that for some x1, xk from G. And then if I take my phi, act on W, it will be phi applied to this, but phi commutes with all these things. So it goes through and hits V. And then I get lambda, right? So it's, let me just not write it all the way. So it will be rho of x1, rho of xk, and then when it hits V, I'll get lambda V. So it's actually lambda times W. So my phi is lambda times identity, and we proved everything. So our goal is to classify all reducible finite-dimensional reducible representations of SL2C. And they should be complex because SL2C. Yeah. So representations of this. And as we know, we have standard basis in SL2C. E is this, F is this, and H is this. And you have relations between them. So bracket of H and E is 2E. Bracket of H and F is negative 2F. And bracket of E and F is H. Yeah, by the way, these are not all relations in SL. Maybe not, maybe. Yes, these are not all. So you still have okay, yeah, now I'm thinking about something that is not needed here. Very well. So you have this, and let us prove the following proposition. So let V be finite dimensional irreducible, maybe even without let me add irreducible, but maybe I even don't need it for this proposition. Irreducible representation of SL2C. Then there exists vector V in V such that EV is 0 and HV is lambda V, where lambda is non-negative integer. Yeah, for that I don't really need this thing to be irreducible. If it's not reducible, then there are more than one vector like that. If it's reducible, then there's only one. And of course, I would like this to be not 0. It goes. Okay, so let's prove this. So idea is the following. So H is very important for us because we built basis in our representation, which is eigenbasis for H. So first step is to choose, so to find an eigenvector, some eigenvector for H. So let W be an eigenvector of H. So HW is mu W for some mu in C. At least one we can find. Then let me take E and apply to W. So I claim that this is also eigenvector then for H. It's easy to check. Let's just check it in a straightforward way. So H acts on this how? So I need to use commutation relations, right? It will be E H W plus the bracket. Since it's a representation, right? By the way, for us, for now, how to understand? So this is just, this is linear operator I apply, and then I apply H to the result, right? So far, it's just some technicality, but we don't know what is H times E, right? Because we don't know what is the multiplication in the algebra. A little bit later, we'll be able to formalize this. We'll have what's called universal enveloping algebra, right? It's not, so if I multiply this in G as matrices, this is not correct, right? Because I don't want to keep relations how matrices multiply. The only relation that I would like to keep in representation is how they commute. Okay? So but this is important.
No, but this multiplication is just in the representation. You know, this is
Right.
matrices.
Right.
And then we use that it's the algebra representation, and so we can use a commutator.
That's true. Yeah. So this one again, I need to actually write something like this. So this is correct. But this is not the same. Might be not the same as this, of course.
Yeah.
But we have a relation that says the following: that I can commute them as things in the algebra GLN commute in representation, right? Because it's a representation. So H, then the commutator of H and E W. So then H hits W gives me mu. So I'll have mu EW. And this bracket gives me 2E, right? So plus 2EW. So it's mu plus 2EW. So EW now is the eigenvector of H with eigenvalue mu plus 2. And I can apply E one more time and one more time. So each time I get eigenvector with different eigenvalue. So I never go back, right? I always raise my eigenvalue. Since these are eigenvectors from different eigenspaces, they are all linearly independent, right? But my representation is finite dimensional.
This mu plus 2 is called high weight.
Yes, it's called weight. I never defined it formally, but we'll do this after this proposition. Yes. Yes. So I apply E one more time and one more time. And every time, if I'm not getting 0, I'm just making more and more linear independent vectors. So since my V is finite dimensional, at some point I should have 0. So there exists some K such that e to the k w is 0 and e to the k minus 1 w is not 0. So let me take this one and denote it as v, e to the k minus 1 w. So this is my vector that I'm looking for. So it is non-zero, and EV is 0. It is an eigenvector. So eigenvector of H. So HV is some lambda, which is mu plus 2k, but we don't care at this point already. So there is some lambda. So the only thing that is left to prove is that this lambda is actually a non-negative integer. So to prove that, we're now going back from v acting by f's. So now we make this eigenvalue smaller and smaller. Okay. So let me take and denote f rho of f to the power k v to be vk, right? Then h vk is lambda minus 2k vk, right? Just the same computations here. I take f, right, commute, and h with f is negative to f. So I subtract 2 every time. Every time I act by f, I subtract 2 from my eigenvalue. And so again, my v is finite dimensional, so therefore there exists some k, right, such that vk is 0 and vk minus 1 is not 0. Right? They're all linearly independent if they are not 0. vk's, I mean. Right? So at some point I should have only zeros, again, because v is finite dimensional. Okay, then let me inspect when such thing can happen. Okay, claim. The following thing happens. The following formula is true. If I take E and then apply, so if I take f, apply to vk minus 1, and then take e. So I go down and then up one step, right? Then this I'm going back to the same eigenvalue, and moreover, so I will get some vector which is proportional, and the it's not obvious as it is, but we will get it. And the value of proportionality is this one. Okay? So let's prove this just by induction. All right. If I take k equals 1, right, so by induction on k, so k equals 1, then this is just v0, which is just v, right? So I have EFV is f EV plus bracket of E and F applied to V. Right. So this is 0. This is H. So lambda V. So let's check. K is 1. So this is 1. This is lambda. Step of induction. So it's base. It's step. Right. So suppose that I know this thing for k minus 2, and I would like to prove it for k minus 1. So I take EF Vk minus 1. Again, it's Fe Vk minus 1 plus H Vk minus 1. All right. Now I need to remember what is Vk minus 1. It was F applied to Vk minus 2. So it's F E F Vk minus 2 plus, and this is eigenvector for this with eigenvalue lambda minus 2k minus 1. No induction assumption yet. So this one will use it. Right, and here it's Vk minus 1. So far I'm just this is how H acts on all this Vk. So this I'm just using this. Right, so now induction assumption, which says that, okay, this thing should be k minus 1, right, times lambda minus k. Minus, so instead k, let me be more accurate. So k minus 1 plus 1, right, times v k minus 2. So k minus 1 lambda minus k plus 2, vk minus 2. Okay, so this is F. F goes through this factor, hits Vk minus 2, gives me Vk minus 1, right? So I have K minus 1, lambda minus K plus 2, and then this thing plus lambda minus 2K plus 2. Vk minus 1. So I just need to check that this thing equals to this. So what I have is this. I would like to have k minus 1, right, times lambda minus k plus 2, plus lambda minus k plus 2, right? And what's left? Minus k. Am I doing this right way or not? I don't know. So k minus 1 plus 1, so it gives me k lambda minus k plus lambda minus k plus 2 minus k. So it's k lambda minus k plus 2 minus 1 plus 1. Victory. Okay, so we proved the claim, but you see, so this is for any k, right? And we say that there should be some k, right? So there exists some k such that k times lambda minus k plus 1 is 0. So at some point, vk is 0, right? So this is vk. Of course, if I apply e to vk, then it's again 0. But vk minus 1 is not 0. So therefore, this factor should be 0. So what we said there is this is happens because we said that there exists k such that vk minus 1 is not 0 and vk is 0. So therefore there exists k such that such thing is 0. It cannot be k equals to 0, right? K equals to 0 is just v. Right? So, I mean, if I take so if k equals to 0, I'm just looking for k greater than 0 because I need this k minus 1, right? So so this is not 0. So therefore this should be 0. So therefore lambda is a necessary non-negative integer in order for this to be 0 for some k, for some integer k. No, k is not even integer, it's something greater than 1. Okay, so we proved the position. Very well. So okay, let me give a couple of definitions. So to use these words. So if we have, if for some v from our representation, it happens that v is an eigenvector for h with eigenvalue lambda, then v is called weight vector. And lambda is called weight of v. Well, of course, v is not 0. So
this definition is given in terms of the cell 2 or in general?
Well, h makes sense only for cell 2 for us now. Yes, yes. So weight is an eigenvalue of h. Okay, and v is a weight vector of weight lambda. So that's the terminology. Okay, and also another terminology that I will use from time to time is that if EV is 0, then such vector I called singular vector. Then V is called singular vector. Proposition. Let V again be irreducible, finite-dimensional representation of SL2C. And let V be singular vector And it is weight vector of weight lambda. And as we learned, this lambda should belong to this.
It's a single vector, it means a vector with weight 0.
No, singular, I mean that it's killed by E.
Okay.
So singular it's the one that killed by E. Its weight vector means that it's eigenvalue for H, and so we actually can find so by previous proposition, this lambda lives in here, actually. So we can find actually, I guess, V such that this lambda lives in here. Then the following is true. So first, I claim that, and it's easy for us from what we learned proving the previous proposition, is that rho of f to the power k v, right, our v case, here k from 0 to lambda. Let me take this set of vectors denoted as b. So I claim that this is a basis of V. In particular, dimension of V is lambda plus 1. And all weights, all possible weights of V, we can just list them. So lambda, lambda minus 2, and so on. And the last two is negative lambda plus 2, negative lambda. So these are set of all weights of V. And two, we actually can prove that V is the only singular vector in V. Okay, so let's see accurately how it follows from what we learned so far. You see, you take V and start applying F, and lambda plus 1, right, is the first VK where we obtain 0, right? VK minus 1 is not 0, but if you take lambda plus 1, K equals lambda plus 1, then you get 0. But before they are all non-zero, and they are all of different weights. So these are exactly list of weights of all these things, right? So it means that they are actually linearly independent, right? So let me put it on board. So first of all, fk of v is not 0 for k from 0 to lambda, and fk of v have different weights. So therefore B is a set of linearly independent vectors. On the other hand, if I consider span of B, it is subrepresentation in V. Right, so all such things, they are just close on direction of E and f and h. Right. Well, we have all the formulas. H just act by multiplication by numbers. By e we goes up with such multiplying by such number, and f just goes to vk with k next index, right? So subrepresentation. So since v is irreducible, span b is just v. And we proved 1. Let's prove 2. So suppose that I have some single vector, right? So let w in v be non-zero such that ew is 0. But then I can now write w as some linear combination of my vk's, right? Since it's a basis. And let me apply e to both sides. This side becomes 0, and here I will have some ak and then f k minus 1v, right, times something. I guess this is k lambda minus k plus 1. So since it's a basis, right, so this is 0 then, right? So since it's this thing is basis, this coefficient is 0, right? So ak times k lambda minus k plus 1 is 0. But k here runs from what? From 0 to lambda. So therefore ak is 0. So this thing is not, I mean, of course I can just start with 1, right? So ak is 0. So of course this is so true if we start with 0, but if I start with 1, this factor is not 0. So ak is 0 if k is from 1 to lambda. And which basically means that w is a constant multiple of v. So v up to proportionality is the only singular vector there. Okay, and finally, okay. So what did we prove? We actually proved the following, that for every reducible finite-dimensional representation V, there exists unique number lambda, non-negative integer, and vector V such that EV is 0, right? V of course not 0, and HV is lambda V. Okay, and so I can now define, so if I have representation, irreducible representation, then I get that I can put into correspondence some non-negative integer and some special vector there. So this vector is called highest weight vector, and this weight is called highest weight of this representation. So definition. Such lambda is called highest weight, and I actually can say the highest weight of V. So V is called highest weight vector of V, and V itself is called representation of highest weight lambda. Representation of highest weight lambda. One more observation before we finish is that if I have two isomorphic irreducible representations, then of course highest weight corresponding to these two is the same. Okay, so let us fix this on board. So suppose V1 and V2 are irreducible representations, and V1 is isomorphic to V2. Then V1 and V2 have the same highest weight. Well, indeed, right? So if you have an isomorphism from V1 to V2, then of course highest weight vector here. So this isomorphism should map single vectors to single vectors, at least, right? So if it's killed by E here, it should be killed by E here. So therefore, and there's only one single vector. So V1, and since it's isomorphism, it cannot be mapped to 0, right? So highest weight vector here is mapped to highest weight vector here by Psi. Right, and so therefore, if I have HV1 is lambda V1, then HV2 is H psi of V1 is psi of H of V1, and this is lambda psi of V1, which is lambda V2. So the highest weights are the same. So what do we get actually? We get, now to sum everything up, so we have a map from isomorphism classes of irreducible representations of SL2 to just non-negative integers. And it just takes V, like some representative in isomorphism class, and gives me highest weight. Of V. So maybe we can denote this map as, I don't know, L. And statement to just conclude our study of reducible representations is that L is bijective.
So L is the map, right?
Yes. So it is bijective because so let me leave it here and start next lecture with this. So not to rush. So it is. We almost proved this, right? So the only thing, non-trivial kind of thing, is to see that it's surjective, right? For every weight here, you have a representation. But we will just give an example, and I think I'll just give it to you as exercise, I guess, for next seminar. Yeah. So it's just the answer is just symmetric power of C2. Gives you like lambda S lambda of C2 is a reducible representation of highest weight lambda. But okay, more about that next time then.